Yeah, thanks for inviting me to give a talk here. So I think some of you have seen. Okay, is this readable? So I will talk about a joint work with Matt Baker, Jun Ha, and Oliver Lorscheid. And yeah, it will be about properties of certain spaces of certain polynomials. So let me maybe first define what the Lorentzian polynomial is. So in this talk, I will restrict to multi-affine polynomials. So multi-affine homogeneous polynomials. So we have some coefficients of indexed by d-element subsets of the set 1 up to n. And these are the coefficients of the corresponding square-free monomials. So this is so these PIs should be non-negative real numbers. So
the didactic choice that you don't allow multiplicities of the integers?
Yes,
okay.
This is a didactic choice, and I will say a few words on how it generalizes if you allow more. Yes, so this the homogeneous polynomial in degree d in these variables. So such a polynomial is called Lorentzian. That there are no squares in the monomials, no squares of variables. So every variable appears to degree at most one. So it can be written in this form. So there are many different ways of defining Lorentzian polynomials. For the multi-affine case, there's one rather simple. So we look at the function defined on the non-negative orphan by our polynomial. And we take the log of the value that our polynomial takes. So positive orphan to make it well-defined. So this is now some function, and we want this function to be concave. So I think this is a pretty nice definition because most mathematicians will understand what it means. So it's a log concavity of the polynomial on the positive orphan. And yeah, historically these polynomials were introduced by Brendan and Hall, and also independently by Oweiss, Liu, Amini, and Vincent. And they used it to prove some concavity statements or log concavity statements on discrete sequences of numbers associated to matroids. So maybe it's not obvious from this definition, but this has this class of polynomials has actually a lot to do with matroids. So for example, we have the following result. So we have such a polynomial, and then we can look at the non-zero coefficients, or more precisely, look at those subsets for which the coefficient is non-zero. And this turns out to be a matroid, or set of bases of a matroid, which yeah, so I will, in this talk, when I say matroid, I usually mean the set of bases of a matroid. So I identify combinatorial object matroid with this set system of bases. So this is, I think this is very much reminiscent of the Blücher coordinates of points in the Grassmannian over some fields. So this is also why I call these coefficients pi. So if you have a point in the Grassmannian over field K, then the non-zero Blücher coordinates of any point in the Grassmannian will be a matroid represented over this, representable over this field. And this is the point of view that we want to take also on these sets of Lorentzian polynomials. Think of it as some realization spaces. So then Martin asked why, or is what happens if these things are not multi-affine. So the most of the, I mean, all of the results will also work in the general case of homogeneous Lorentzian polynomials, but then one has to replace things like matroids by M-convex sets.
Your definition still hold if I leave multi-affine?
No. Yeah, I mean, there's a, like, you would have to require that any derivative in coordinate direction is log concave on the positive. So some people call this strongly log concave or something like this. Yes, so let's define the spaces that we want to look at. So Lm should be, so M a matroid, be all polynomials whose support is this given matroid, which are Lorentzian. So you can define for every matroid of rank D. So the rank of the matroid will be the degree of this polynomial on 1 up to n. And right, so like the Grassmannian lives in projective space, so the Blücher coordinates of a linear subspace are only well-defined up to global scaling. So in this spirit, we look at the projectivized version of this set. So this is yeah, the projective equivalence classes of our polynomials in this projective space of polynomials. Okay. So I said that we want to think about these spaces here as some sort of realization space. So let's relate it to some known or some classical realization spaces like Grassmannian. So we look at the points in the Grassmannian of D-planes in n space with non-zero Blücher coordinates. Are indexed by M. Right, so we already said every point in the Grassmannian defines a matroid by looking at the non-zero Blücher coordinates, and we fix some matroid and look at all points that give rise to this matroid. So this could, of course, be empty for some, is empty for some matroids M. But we always have a map from this Grassmannian to Lorentzian space, which maps couple of Blücher coordinates to the polynomial whose square is whose coefficients are the absolute value squares of these Blücher coordinates. Okay, so this.
Do you need to use like the Blücher equations to show that the property holds, or is just something you could do for every point projectively? I mean, you know what I mean?
You don't use, second question, no. First question, also no. So you take a representing matrix of this thing, and then so let's say you have a point here, X, and it's given as the row span of a matrix A, of a D times N matrix A. And then you look at this polynomial. And then it's like some determinantal identity. Well, it's a Hermitian conjugate. Then some determinantal identity says that the result will be exactly this polynomial. And then you can prove Lorentzianness by using this representation. So yeah.
You can do it from like a hyperfield point of view. Yeah. There's a hyperfield structure on the right-hand side, which implies Lorentzianity.
I will get to this, but there's the relation to the hyper. You mean the triangular hyperfield? Yeah. So this, I will get to this. Yeah. Here, you can use like the determinant is log concave and then things like this. Okay. More questions? More comments?
So you said you will get some in Geoemtry, but not all. So you have this map from the.
Yes. So this will be why you cannot get all. This will be clear like in a few moments, I think. So there's another example. So we look now at the Dresden of a matroid. So this is all real valued functions on the set of bases of M, which make this valuated matroid. And then you mod out the constant functions. by like as the linear subspace of the space of all functions, and constant functions always make it evaluate matrix. So you can mod this out, and then you get the following map to, what is this? To Lorentzian polynomials. So if you take the log of the coefficients of a Lorentzian polynomials, or look at this space in log coordinates, then it contains the Dresden. And this means that this space is always non-empty, because you can always, for every matroid, the constant function is, or the zero function makes it evaluated matroid. So this thing always has a point. So this thing is always non-empty. But the Grassmannian, like this, who asked this? Oh, yeah, sorry, you asked this question. So Grassmannian MC might be empty. It's empty for matroids that are not representable over the complex numbers. Let me make one remark. So it's always helpful to look at things modulo some group action maybe sometimes. So if we have a Lorentzian polynomial, then we can scale every variable by some positive constant. This will not change the support, and it will also not change this thing being concave, right? Linear change of coordinates. So if I draw pictures, then I will draw them modulo this group action of scaling, and also in log coordinates. So this in log coordinates, this scaling is just some addition of certain vectors, and yeah, and by log coordinates I mean like take coefficient-wise coordinates, so that the Dresden really sits inside this space as a piecewise linear object. And then I can draw an example. So let's look at the uniform matroid on 4 elements of rank 2. So in which dimension would I draw this? Who has a guess in which, if I stick to this rule? So, exactly. So 2 dimensions. Why 2 dimensions? So there are, so how many parameters we have? It's 4 choose 2, 6 parameters, but then I draw modulo scaling, and therefore scaling parameters. So then we have the Dresden, and we can look at the image of this map, so of the complex Grassmannian, but we can also look at the image of the real Grassmannian. This will be, we'll have 3 connected components. And then hard to distinguish which what.
Super bad.
You want this? Is this better? So this will be the region bounded by the image of the real Grassmannian, and this also, in this case, the space of Lorentzian polynomials. So in this case, the image is everything, but in general, the image on this map is everything. In general, it's not.
Is it for the uniform matroid in general, or not even that?
Not. So for the uniform matroid, this the dimension of this will always be n choose d minus 1, but the Grassmannian does not have this dimension. I mean, it is. So, yes. Yes. So in this case, it's an amoeba. Amoeba of the in log coordinates, it's the amoeba of the complex Grassmannian. And from this, I mean, we can also we can see what is the topology of this space, let's say modulo scaling. So it's a disk with 3 points removed from the boundary. The 3 points correspond to the rays of the Dresden. So this will be the case always up to some just one point is different. So in here we did the naive count of parameters, and we deduced, okay, this should be two-dimensional image. This is in general not the case. There are some constraints. Where did I put the? This is essentially due to Bendin. So if we have a Lorentzian polynomial, these for some matroids, these things will satisfy some relations. So namely, we let J be some d minus 2 element subset, and some further indices I, J, K, L, then one of the following 3 real numbers. So these are, write down, are the 3 terms of the 3-term Wicker relations. And the statement is, if for a Lorentzian polynomial, if one of these 3 real numbers is, so I think Alex could complete the sentence where he's nodding. So if one of these 3 is 0, then the other 2 have to be 0, equal. And it's, I mean, looking at this example, this is not very outlandish, this condition, right? So if it comes from a point in the complex Grassmannian, then its Blücher coordinates satisfy this minus this plus this is 0. So if one of these numbers is 0, which is equivalent to its absolute value square being 0, then the other ones must be equal up to a sign. And since we take absolute value, the other ones have to be equal. And in the same way, one could derive this condition for the Dresden. This is not probably not surprising if we think of it in this way. And so these are some binomial conditions which depend only on M. If we look at it in log coordinates, these are some linear conditions that depend only on N. So in general, in log coordinates, the PLM will be contained in some combinatorially defined linear subspace. So we cannot expect it to be full dimensional, but we will see it in this subspace, it's full dimensional. But before I get to this, I want to discuss the triangular hyperfields that Alex already mentioned. So these are a way to put all these comments into a common framework. I will not define what the hyperfield is, but I will. We will not need this for this definition. So we just define for 3 non-negative real numbers and some positive number q. We define, so for every positive number q, we define a relation on 3 non-negative numbers. And we denote this relation by like this. So this is some relation on 3 elements, so it can be true or not. And it's true if and only if the qth root of these real numbers form the side length of a triangle. Okay, so this is just something for every q and x1 to x3, something that is true or not. We also want to go to limits. So for q equals 0, we want this to be satisfied for every positive q. And we can also go in the other direction, q infinity. And we just want it to be satisfied for some positive q. So and then we can act like these things, these relations are really equations and define the Grassmannian for this type of addition by saying some coordinates pi are in the corresponding Grassmannian if these three non-negative numbers satisfy this relation. So for matroid M of rank D on n elements, we define the Grassmannian over the fused triangular hyperfield. So there is actually some algebraic structure called hyperfields, and then this structure, this is this really makes sense, and this is the addition of these hyperfields, but this I don't want to define. Yeah, so all pi so pi non-zero if and only if I is an M, and for all j as in this example before, and distinct additional for indices, the hypersum of these three numbers is 0.
There's some kind of example triangular hyperfield we should think of to make this make sense for us.
Yes, but not, I mean, yeah, let me, yeah. I mean, the Q equals 0 is a very familiar, but it's not the typical one. All the other ones are, and also Q infinity is special, but all the other ones are kind of the same. So just, yeah.
You can think about Q equals 1, for example.
Yeah, that's maybe the typical one. Q equals 0 is the tropical one. So I will, yeah.
Say that three numbers. Okay. So tropical would be saying that minimal lengths are equal.
Maximal. So yeah, let me discuss it. So maybe first see how it relates to this example on top. So if we have three complex numbers which sum up to 0, so for example, if the three terms of the three-term Blücher equation of a complex linear space, they sum up to 0. So this is the complex plane. This just means that these are the sides of a triangle. So if we take absolute value, then this is 0. So we get actually a map to the absolute value map. Just sends, maps the complex Grassmannian to this. So, I mean, this is one way of approaching the fact that the limit of amoebas is the tropicalization. Because so these, if these Grassmannians over TQ, they get smaller and smaller, the smaller Q is getting. So if P is greater than 0, then P is greater than Q, then this is. So if we draw this in log coordinates and or if Q goes to 0, then this Grassmannian set will get closer and closer to the Grassmannian over T0, which is a familiar object because this is the tropical hyperfield. So if there's something one can easily calculate, so this is, I will not do it here. So this relation over for Q equals 0 just means the maximum is attained twice. I mean, if the maximum is attained twice, then we can always make it a degenerate triangle, which looks like this. So this means this is really the log map defines a homeomorphism from the Grassmannian over T0 to the Dresden. And the T infinity can also be understood. This is so one can check that this condition really just means this condition that we have here. So if one of x1, x2, x3 is 0, then the other ones have to be equal. Right? So if one edge length is 0, then the other two edge length of the triangle have to be the same. So we get what we get here is that the logarithm. So this result by Brandin can be rephrased as the set of Lorentzian polynomials lives inside the Grassmannian over T infinity. Or if we want to look at log coordinates, then this is homeomorphism to this linear subspace. So this is the this general point of view, which fits these things into one
And on point 4 there, is this LM?
Which one?
The last thing you wrote, and so is this LM on the right? The Lorentzian?
VM. So this is, so these equations, they define, there's a binomial equation. So if you take log, they will define a linear subspace. Image of the point satisfying these relations will be a linear subspace of under the log. This is now I can maybe answer Alex's question, namely how are these Grassmannians over the triangular hyperfields related to the set of Lorentzian polynomials. So unfortunately, it's not equality, but we can always sandwich the Lorentzian space between two triangular Grassmannians. So for every matroid M, there exists a positive Q such that and here yeah, I forgot to say this again because it should be Grassmannian. We only look at it up to scaling every variable. So we have, we don't have equality, but we have this this sandwich theorem. Unfortunately, it's not like this is really this Q. There's no universal Q which makes this true. So for every matroid, there might be another Q. Or we have a sequence of matroids where this Q has to go to 0. This theorem explains two of the examples that we had before, because this one for positive Q always contains the Grassmannian over T0. So this explains why you can map the Dresden inside here. And T2 is, of course, contained in T infinity, which recovers this result by Brendin.
The sequence of matroids with Q goes to 0, that they are the same rank? They have the same rank?
No.
No.
Yes, they have rank 2. There's a sequence of rank 2. That like the uniform matroids of rank 2 are the sequence. Yeah.
If I fix D and N, can you give me a bound on Q that works? In terms of D and N, that will always work.
Yes. No, I mean, I cannot give you an explicit one. Yeah, sorry. But yeah, for
Is every Q between 2 and 0 the lower bound of something, or are there like restrictions on what Q is?
yeah, okay. So this for making just this statement true, one can look at the U24. In this case, one has equality. So in this case, the statement becomes true for every Q between 0 and 2. But maybe the question was more like, can every...
This exists.
You mean the optimal Q? Yeah, this... I mean, it cannot, not every Q can be this, because there's only countable number of matroids, but incountable many real numbers. Yeah, that's a good question. I don't know. So Q equals to 1 maybe let me this it's just some facts that we know. So if n is and then for, I mean, we know very little, so yeah. So we know very little, but we know that for n equals 5, q equals 1 is okay, and we know for n equals 8, q equals 1 is not okay. Don't know what happens in between. We conjecture that, or not, I mean, no, I don't know if we conjecture, but we tried hard to prove this also for 7 and 6, and we failed, so maybe q equals 1.
Do you expect that we take the supremum of the q's, you'll get equality?
Of these, no. So whenever m is representable over the complex numbers and the matroid doesn't have a U2-4 minor, then, or sorry, U2-5 minor, then this thing will intersect the boundary of this. So there will be, but it cannot always be q equals 2 in these cases. So at these rays, there will be a gap between the supremum q and so this.
Boundary intersections.
I would say yes. I mean, they contain the image of the complex Grassmannian. Yeah, maybe this would be somehow interesting whether this is a characterization that's always there. Okay, let me write down one result on the topology of PLM, which I motivated already here. So in this example, it was disk with the 3 points removed, 3 points corresponding to the rays of the Dresden. So this is basically what happens, but it's not always full dimensional, but it's full dimensional in this vector space defined by Brendin's relation. So we look at the unit ball, closed unit ball in this space in linear subspace in log coordinates, then our space is homeomorphic to this ball minus take out things from the boundary, those that intersect, the Dresden intersects the boundary. And it's also homeomorphic to these Grassmannians. So this.
Look contractible.
Hmm?
These Grassmannians look contractible. Exactly.
I mean, some points at the boundary are missing.
Ball length. Okay, so I was confusing ball and split.
Ah, yeah, ball. Yes, ball. Yeah. Yeah. So this shows, for example, I mean, it shows what the dimension is. So it's the dimension of Vm, and this can be expressed in combinatorial terms. It's the rank of the Hut group of M. And it also shows that this space can be compactified to a ball. It's
Type of homomorphism. Do you know what is the type of this is a homomorphism, but how does it look like? Do you know it?
Yeah, you go into log coordinates, and then you and then this it looks basically like this. It's a star-shaped. You take the circle, and then you for every ray you scale, you go up to the boundary, and then you scale it back to the
Do you know what is the shape of the boundary? The Grassmannian intersection with the boundary? This we don't know.
I mean, we know it for some examples, but I mean, the Dresden can be pretty complicated. In some cases, it's at least a little bit more tractable than this semi-algebraic set. But in general, it's very complicated.
When you wrote that equality there with Grassmannian MT2, that's supposed to be an inclusion only, right?
In this case, it's equality. So this, in the special phase, yeah, exactly. In U24. In general, it's only inclusion.
Maybe the obvious question is PLM B points of a Grassmannian for some hyperfield B or some band B? Or
yeah, I don't know. You mean very suitable chosen?
Maybe put this some algebraic statement in the background. Let's say that your space of Lorentzian polynomials is rational points of some Grassmannian in some appropriate sense.
Okay. Oh, so
And this is saying like this hyperfield B is some sort of limit of this CQ.
So there are different. So there are many different ways of this. I mean, basically, like two ways of defining what is this over hyperfield. So there's like strong matroids and weak matroids. This is weak matroids. This is only three-term Blicker relations. And for this, for weak matroids, we can say, okay, it's not. You cannot define, cannot characterize Lorentzian polynomials by only looking at contractions to 4 variables. So in this sense, no. But maybe for like this result also is true for strong matroids with satisfying all Blicker relations. Then the 2, we have to remove the 2 by some possibly large number. And there I don't know immediate answer. Yeah, let me maybe.
Strong is a stronger condition, so shouldn't it get smaller? Shouldn't the set get smaller if you say strong?
Strong is a stronger condition, so this set is smaller, becomes smaller if. Let me. Yeah, I mean, we can also do some discussion. So, more questions?
That you associate to M, is it increasing with respect to minor property or something? I mean, is it some by contraction relationship? Is there that have you monitored in terms of the usual operations on words?
Okay, you're saying if we take a.
For example, if you want to see, you look at the metroids where
Yes.
it's bigger than the.
Yes, yes, it's mine. Yes, yes. Okay, so maybe some more things about this topology. This lets us compute the compactly supported Euler characteristic of our space. So this is like it extends the usual Euler characteristic for compact sets to certain nice class of possibly non-compact sets by inclusion-exclusion. So here we can compute the Euler characteristic of this by this formula. So it's one so Euler characteristic of the ball minus, and because the Dresden consists of rays, this is don't go into details. This is also the compactly supported Euler characteristic of the Dresden. So at least, I mean, still this is a very complicated object, but it's piecewise linear, so there might be more chance to calculate this. And maybe in the last few minutes, so here we have seen that this is this can be compactified to a closed ball, but there's one natural or naive compactification, which is that it lives inside some projective space, some real projective space, which is compact. So we could just take the closure of this inside this real projective space, and one could ask is this naive compactification homeomorphic to a ball? This was proven by Brendin for uniform matroids, and he asked whether it's true in general for every matroid. And this was maybe some sort of very initial motivation of this project. And let me just explain two cases. So question by Brendin. So if M is binary, then the answer is yes, and for simple reason, because in this case, one can show that modulo scaling, this set is just a point. And since this set is inside this set and non-empty, it's just the orbit under the scaling operation. So this is then orbit closure, and then like for the moment polytope in toric geometry, get that this is just in fact just the matroid polytope in this case. And I don't have a lot of time left, so we look at the matroid of rank 3 on 11 elements whose non-bases all 3-element subsets whose indices, whose elements sum up to something divisible by 11. Then using this formula here, one can calculate that. I mean, using a computer, one can calculate that this has compactly supported Euler characteristic 11. So it's not a ball in this case. And now the time is up. Yeah, thanks.